Hi everybody. So welcome to this virtual class today. I appreciate you all being here. So over the last couple of lectures we have learned how to add different things to carbon-carbon double bond, right? Things like water in different ways, either in Markovnikov fashion or anti-Markovnikov fashion, or things like HCl, HBr, right? And so now today we are going to learn how to add different things. And you're going to start by adding hydrogen, H2, to a carbon-carbon double bond. Okay, so this type of reaction is called catalytic hydrogenation. And so the tricky part of this reaction is that, we're going to look at how hydrogen is going to add to a H2 is going to add to a double bond, and the tricky part is that H2 is held together by a really strong sigma bond, right, between the two hydrogens. So of course you should be able to draw the orbital diagram, right, with the sigma and the sigma star antibonding orbital, and the two electrons in the sigma orbital. We talked about that a while back. So now this bond for H2 is so strong that we need to use a trick. And so we actually need to cut this bond. And so we need to use a special catalyst, usually palladium or platinum, to enable this type of reaction. Okay? And only with a catalyst you can add H2 to a double bond. I'll give you some time to write this. Now recall, what does a catalyst do to a reaction? We have seen catalysts before, we're going to acid catalysts, right? Which if you use acid, it can allow water to add across the double bond. Right? And what a catalyst does, you've seen this before, is it lowers the activation free energy of a reaction. But the key is that the catalyst itself, of course, does not get consumed. So I want to show you again with a reaction free energy diagram, right? So that you never forget this. So we have G here on the y-axis. G is the free energy, right? Delta H minus T delta S. And here on the x-axis we have the reaction coordinate for the reaction. So this would be a typical reaction coordinate for a reaction without a catalyst. And you see the activation energy there highlighted in gray. That's the activation energy without a catalyst. Pretty high. Now with a catalyst, a different reaction pathway takes place. And so we get usually more intermediates, and overall, you see the activation energy for the reaction with the catalyst is now lower. That's the key. You have a lower activation energy with the catalyst. Give you like a couple seconds to write this all down. So now, next, how exactly does the catalyst for catalytic hydrogenation function? First of all, it's a palladium or a platinum catalyst. And this usually this palladium or platinum metal, which is very, very expensive, or my wedding ring is made out of platinum. It's usually attached to a porous carbon surface. So something like graphite, but more porous, right? Porous carbon. And why do people do that? Number one, they do it to enlarge the surface area of this so-called heterogeneous catalyst. The catalyst is not dissolved, it's just suspended in the solution. That's why it's called heterogeneous. So the larger the surface area, the better of a catalyst it will be, the more accessible it is by the substrate. And so then this in turn increases the reaction rate, the reactivity. And finally, finally this reduces the cost. These type of catalysts are very, very expensive just because it's very rare metals like palladium and platinum which are involved. Okay, so remember, attach it generally to the metal to mix it up with a carbon surface. And so this is called, this is usually called palladium on carbon or platinum on carbon. Sometimes platinum is used just by itself. And it's written as palladium PD/C. That means palladium on carbon, attached on carbon. Right? And so here's how the catalyst works. We have here in gray, this is just symbolizing the catalyst surface. Catalyst surface. And now what happens first is H2 comes in. It's a gas, right? It's just getting dissolved in the solution. And the palladium metal or the platinum metal on the surface is able to split apart the H2 bond. It's pretty amazing. So first the catalyst weakly binds the H2 and then it splits the molecule. And it binds two individual hydrogens to the metal surface. So here's how it looks. I'll give you a couple seconds to draw it. Here's the metal surface again. And yeah, so now here we have two individual hydrogen atoms. I extended the metal surface a bit on the right because we need to now draw. Next, we need to draw an olefin. At the carbon-carbon molecule with a carbon-carbon double bond will actually weakly coordinate again to the metal surface first, because the double bond, as you all well know, is nucleophilic. The metal surface is actually electrophilic. And so that's what happens. It kind of weakly binds the olefin first. And then here's the next thing which happens. Now you see that then the olefin really attacks as a nucleophile the metal surface, and then that makes a formal carbocation on the left side there, on the left carbon of the olefin, and then an H hydride shift kind of occurs. Okay, and it leads to a new product again on the metal surface, right, where we now have this product here. On the left side we already have a hydrogen kind of inserted into the double bond, and on the right side the carbon itself is now attached onto the metal surface, right? And what happens next is now this carbon metal bond is electron rich. So it acts as a nucleophile and it deprotonates the surface, the hydrogen on the surface. And it gives an electron back to the surface. Okay, and so finally, then that liberates the catalyst, the original catalyst surface. And it liberates the hydrogenated alkene. You see, that's the alkene where two hydrogens have been added to it. And so, important thing is here we have the regenerated catalyst. Right? Give you a few seconds to finish up the writing. So if you have any questions, now would be a good time to ask Kyle. So next, the catalytic mechanism. See, what happens is both hydrogens actually get attached from the same side. So it leads exclusively for hydrogenation. Catalytic hydrogenation leads exclusively to so-called syn addition. It's very important. So syn addition means that both hydrogens, or both things which attach to the double bond, they attach to the same side of the double bond. All right. Let's practice a bit. Try to predict the products of the following reaction. Here's the reaction. We have an olefin, and we're using H2 on palladium carbon. And the question is, what products do we form in this reaction? So take a couple minutes and try to draw the products. Make sure you draw both enantiomers if enantiomers are forming, and try also maybe think about the mechanism as well. We'll reconvene in a couple minutes to look at what the actual products are.